much for introducing myself. Probably a few of you have seen the picture of me from Brussels in the morning. I was really worried about myself, and I was feeling quite comfortable that a lot of physicians were around. I looked very bad at this slide, but I'm still alive. So what we are going to do now is to go into details about CT analysis. And what I would like to do together with you is to make a short journey how CT is applied for scientific reasons, if we talk about thorax CT, and what informations we can get as a tool for therapeutic and diagnostic options. Well, if we look back at this history of CTs for thorax imaging, the guy who brought up the CT scanning for thorax imaging was finally Göran Hedenstierna. And the very first animal he was looking at was a pony. So, of course, if you look at a pony, it takes some time to bring these results back to human practice. And I would just focus that up to this point, the only thing that was available was thorax chest X-ray. And we know now from the application of CT scans that it makes a large difference if you look at a normal thorax CT X-ray, at a normal thorax X-ray, or if you look at the CT at different levels, starting from the apex and going down to the diaphragm. So what we learned, that there are regions which are well aerated, which are normally closely linked to VIQ regions above 1, that we have poorly aerated but potentially recruitable areas with low VIQ or typical low VIQ areas, and that there are non-aerated, non-ventilated, true shunt areas. Probably we can describe them as consolidated areas, which we, as we actually learned, know that they are equal in recruiters and non-recruiters that can potentially really not be opened up. So what has thorax CT and the use of thorax CT has taught us over the years? First, it had brought insights in the pathophysiology of LI and RDS, and I would quickly like to mention. So we learned that this is an inhomogeneous distributed disease. We learned that there are, especially if a patient is in supine position, that there is a ventrodorsal and a craniocaudal gradient. We learned about gravity dependency. We learned about superimposed pressure, and we learned about responsiveness to PEEP. So in the very beginning, there was this guy who was the first to apply it to human beings. And if you follow together with me, so this is where for the very first time of density in the dependent regions of the lung, assuming that these were representative samples of the whole lung, even the right computed from the mean CT number and lung and gas volume. Just as an aside, at that time, Antonio Pesenti called himself Antonio Presenti, which is still in the med line. It's not a wrong spelling by me. It's really in the med line. So, okay. And there was another publication, and they described for the very first time that changes in aeration induced by PEEP can be described with the means of CT. So what we normally now know is that there is a distribution starting off of minus 1,000, so minus 1,000 with up to minus 900 Hounsfield units means overinflated lung areas. And we learned in the morning that starting from minus 900 up to minus 100, this is normally and poorly aerated areas, and everything between minus 100 and plus 200 is not aerated or consolidated lung areas. So the normal distribution in a healthy lung would look like this. So most of the areas, and this is again a Gaussian distribution, is in the normally aerated areas. So if we now look at an RDS lung, the distribution or the shape of the curve of the distribution of density looks like this. So there is much more a distribution in the areas of non-ventilated or consolidated lung areas. So now let's have a careful look what happens if we apply PEEP to such a lung. And you can see this is now an oleic acid injury model in a sheep. What happens if you apply PEEP? So first you have baseline. It's more or less looking like the healthy lung you have seen before. Then you add lung injury, and you add it at SEEP, which is a red line. So the highest point is here. And then you increase step by step PEEP level from 7 to 14 to 21. And if we look at the according CT scans, it's looking like this. So this is SEEP after acute lung injury, and this is at the highest PEEP level of 21, which means we are actually at least able to shift this curve a little bit from non-aerated to the aerated parts of this Hounsfield density distribution. So first of all, what can we do while applying CT analysis? We can do what we would call a global analysis. And there are some tools available. This is just what we see as a blue line here, and it is drawn here as green and as red with injury and without injury. So you can see you can do over the whole range of the lung, from the apex down to the base of the lungs, a distribution of density. And the blue line is the median value of those values you can get over all these ranges. So what you can do in addition is you can do regional analysis. You can look at the air content, the air tissue correlation, and you can define by calculation, I will very briefly go into that, the lung mass. And you can do an automatic segmentation of the lungs. You can divide in left and right lung, and you can choose 4 segments, for example, 1, 2, 3, 4. However, now it starts off to become problematic, and Luciano already went into this discussion. If you say, now let's look for 4 ROIs, regions of interest, how to define? Should we define them in centimeters, which means you look at different volumes, or should we say the definition should be we compare comparable or equal volumes, which has to be defined in advance? So what we can do additionally is we can do dynamic analysis and reconstructions, for example, of the diaphragm. We developed a special tool which allows us, if you go slice by slice through the lung and you look at the boundaries of the diaphragm, you can do through the slices a reconstruction of the shape of the diaphragm. Another thing you can do dynamic calculations. And for that, you use ultra-fast CT going up to 20 hertz, and then you're doing it in one breath and in one slice, which means you look more or less, because there's a movement in the thorax, it's not every time the same place, but you look more or less in the same place. And then you get a sequence of CTs like this one. Then you can look do your calculations indices, or looking for the amplitude, the maximum Hounsfield number, the minimum Hounsfield number, and then you can look for the regional density changes, and it gives you a picture like this, breath by breath. Maximum Hounsfield change up and maximum Hounsfield change down. And this is work I have done together with Norbert Weiler, who is actually in Kiel, but this was work which was done in Magonza in Mainz. And we were looking for different things. Alveolar cycling at mean airway pressure of 23 at SEEP in a non-injured lung. And if you just look with me, so this is dynamic. The use of dynamic CT images to demonstrate, well, there is alveolar cycling. If your mean alveolar pressure is 23, you use a SEEP level of PEEP, and this is a non-injured lung. So now let's look what happens also in a dynamic way if we look at an injured lung and we apply very fast, with a very fast flow, a pressure of 50 centimeters of water over a period of 11 seconds. And what you now will see is the time constants that are used to open up. So if we look at this, so it starts off and it's opening, and there's over the whole period of the 11 seconds, you find re-aeration, recruitment, and opening. So this means you can show that reopening is a time-dependent factor. So this is to do something very useful in the afternoon to keep you awake. What I would like to do now, I would like to carefully go through all these equitations with you, just to show you, because there will be an examination about these calculations as well at the end. Now, what I would like to show you is with this, what you can do, what you finally can derive if your assumptions are the density of air is minus 1,000, the density of water is 0, and then you look for the voxel, which is the smallest CT unit of the lungs. And then you start off calculating the gas volume. You can look for the total gas, the tissue volume, and of course you can do all the calculations with well-defined, internationally accepted equitations. So what is thorax CT actually used for? It's used for identifying underlying pulmonary disease, no question. It's used for identifying recruitment and overinflation. It's used to identify dynamic changes, for example, alveolar cycling. It's used for identifying of effects of extrapulmonary changes. I will give you an example for that later on. And it's used for the validation of respiratory parameters, of EIT, electronic impedance tomography, stress index, and as a tool for setting the respirator. And as I have showed you with the diaphragm, it can also be used to reconstruct part of the lungs or even the diaphragm. So that's what you have learned before, and we have learned, I used the old definition that we probably have to change our mind with about what alveolar recruitment really means. But easily said, spoken, it's a process reopening a formerly a non-aerated area of the lungs. And the gold standard, I'm trying to convince you, is still today, it's the CT analysis. Probably it's better to say the amount of gas that can even at a given airway pressure be detected in a formerly non- or poorly aerated lung area. And as we have learned, probably we can just put away in a non-aerated area because we learn it's not openable. So this is very old. No, it's not very old, but going back to 1995, because if you read your own publications, you always realize that you are getting older and older. So it's very young work of Luciano Gattinoni from 1995. And what he was looking for in this was, while using a given plateau pressure, how much PEEP is necessary to keep the changes expressed as recruited gram of lung volumes open at an expiration. And you can see there is a large difference. And if you use a pressure of 46, you use as a plateau pressure, you nearly need a pressure of PEEP level of 20 to get alveolar closing and cycling nearly abandoned. So that's something which has been shown and proven while using CT scan analysis. You have already seen this. You can show along the pressure volume curve there is recruitment. There is even recruitment above the upper inflection point, going up to the total lung capacity, and this has been shown, clearly demonstrated by CT scanning. We have also learned from this study from our friend Paolo Pelosi that tidal volume recruits. You see PEEP level of 5 or 15, and the only difference between these two lines is low tidal volume, medium tidal volume, and high tidal volume. And once again, be very careful about the PaO2 that is resulting. Maybe we put a lot of stress and strain to these lungs, but nevertheless, there is a high PaO2 resulting. So you can use it to set settings for different respiratory respiratory modes. This was a study we once performed to look what might be an ideal tool to find out which is the right continuous alveolar distending pressure while using high-frequency oscillation. So again, you can use CT scan to verify and validate if this is an optimal point of recruitment while you are applying a specific alveolar distending pressure. So this you have seen in the morning. Also this technique, the stress index, I go quickly through because you are well aware now, has been validated, as you have seen, while using CT scanning. And you learned an additional information. You learned that the stress index alone would never ever allow us to define between this state and that state. It's the same stress index. However, CT thorax demonstrates there is a large difference. This is a totally opened lung, and this is a more or less collapsed lung, at least in, let's say, 1/3 to 2/3 of the lung. You can also use CT scanning to demonstrate that if you're using spontaneous breathing attempts, this is work by Hermann Brigger from Christian Puttensen's group, that you can show there is again a left shift of the density distribution, showing that there is more recruitment while using spontaneous breathing attempts. Well, I originally told you that there are also hints that you can demonstrate the effects of extrapulmonary changes. So we have learned that pulmonary and extrapulmonary IRDS finally are different, at least with regard to intra-abdominal pressure. So you have already seen more or less these slides. This is the same pressure applied in oleic acid-injured lungs. And you see with a pressure of 40 and an abdominal pressure of 0, there is nearly total recruitment by applying a pressure of 40. However, if you increase the abdominal pressure to 20, you apply the same airway pressures. This is not transpulmonary pressure, this is just airway pressure. You can realize that there is nearly no recruitment. Same pressure applied, totally different behavior of the lungs. So one of the reasons might be there is a change in transpulmonary pressure. This is true. However, what we learned in this study, that there is something in addition. And this is a marked fluid shift, a marked increase of excess tissue mass, which is distributed all over the lung, even in the very upper parts of the lung. So if you look along the lung, there is a marked increase in edema formation, even in the very apical parts of the lung. However, you can use, because we had to fight a long fight with the reviewers of this paper, because the reviewers told us, well, that's nice, it's a nice performed study. However, what makes you sure that the observation you made, that there is a marked increase in edema formation, is not dependent from the progress of oleic acid injury? So now we use CT scanning to prove that this is not true. And what you can see here is the edema formation over time. And you see there is a clear decrease. So the edema formation caused by the oleic acid injury itself is not responsible for the changes we have observed. So you see it for different time points, 30 minutes, 75 minutes, and 150 minutes. There is nearly no change in edema formation. And now we look in pigs that have only oleic acid injury, nothing else, no increase in intra-abdominal pressure. So this was the proof that was accepted finally by the reviewers, but it could only be done by finally finding out the increase of edema formation while using CT scan techniques. And you can also use CT scan techniques to find out what are the long-term changes in the lung. This is a nicely done study by the group of Peter Suter, which finally demonstrated that really in the most upper parts of the lung, close to the sternum, there is a highest injury if you look over time. And you can prove this with the amount of bronchiectasis and changes in the lung, which is going up in the segments 4 and 5, and this has been also been validated while using CT scanning. Well, but where the thorax CTs has its limitations and problems, so repeatability. So it's nevertheless radiation you use in a human being, if you use it more or less to control what you are doing. And even if you don't look at the radiation, it's staff-consuming performance and analysis. We didn't talk about the analysis. Those analyses I've shown you take hours and days for many, many people. So, and at the same time, it's necessary to transport the patient. We have an ongoing discussion, is it sufficient to use only 3 slices, or do we need really whole lung CT scans to really make a good prediction of what's going on? And this is a sentence that has been formulated by Luciano a few years ago, and I just show you what it really means. The CT pulmonary unit voxel does not allow to discriminate directly the nature of the density of changes, which you can observe. I will show you in a few seconds. And if not used for diagnostic reasons, thorax CT is of limited value for acute clinical changes in practice. That's why I'm convinced of. So anyway, this has been done by Luciano and a drawer from Luciano a few years ago, and shows you what might be represented in such a voxel. So you might have a fluid-filled area density, you might have a collapsed area, you might have an opened-up area, and you might have an over-distended area. And you are not able to say, well, if you observe this in a voxel, this might be a normal inflated alveoli and overinflated alveoli. This might be a collapsed or fluid-filled region, and you are not able to do a sufficient discrimination by just looking at the CT scan. Well, this is from Wolf, and this is again to make us aware it plays a role if we think of what we are applying to the lung, to look of what is really underlying. Is it more interstitial edema? Is it intraalveolar edema? And we are normally not able to do this discrimination while using CT scan techniques. You might also use CT scan techniques to identify overinflation. This is from the group of J.J. Ruby, which has clearly demonstrated that it's also dependent from the underlying disease if you find overinflated regions or not. We can skip that. So why is this in this presentation? Why doesn't the elephant have a pleural space? Well, it's just to make you aware that there are species differences. And if we talk about numbers, and if we look at results from different studies, be all the time aware that it's simply a model. We try to do something in a model, and it's totally different what we might observe in human beings. And this is just, it's a nice, if you have the time to read it, it's a nice study showing that an elephant has no pleural space because he's able to snorkel. And snorkeling means he needs some special adjuncts of his lungs to the thorax wall. So it's, if you would like to look, for example, for pleural pressure, an elephant is not an elegant animal to look for that. So the question is, are we looking for the right things? So this is now for the female in the room. That's where men are looking for, and that's what looking for us. So this is again what I have showed you before. And once again, I don't want, because Luciano went into details, in one of the most amazing things was both groups, high potential for recruitment, low potential for recruitment, showed the same amount of consolidated lung areas. And the difference was only in the amount that can be transferred from non-aerated, from poorly aerated to better aerated areas. So now, and I finally would like to close with looking at two different techniques very briefly. They are selected just for my choice because they are more or less actually available at the bedside. So what should a good or ideal procedure to do to identify recruitment at the bedside? It should really measure recruitment. It should compare to the gold standard. It should be easy to perform. It should be repeatable and reproducible. Should provide information at low cost. This is also an argument if we talk about CT scanning, and should cause no adverse effects for the patients. So very briefly, EIT technique. So this is electrical impedance tomography. Finally, you do nothing else than injecting a current, and you go with this injecting current by using 16 electrodes around the thorax. So this was one of the studies we have done when I was still in Mannheim. And what we did, we looked at CT scans and tried to compare if we can describe the same changes in density as the same changes in delta by using EIT technique. And you can do, you find something comparable, but you have to be aware. If you look at EIT technique, this is not really representing an anatomic field. It represents a cylinder. So, and one of the discussions with the reviewers we had with this paper was, what makes you sure that you are comparing the right things by looking at your EIT slice and looking at your morphological slice from the thorax CT scan? However, what we know, we can describe changes in density, and they look very much like the changes in delta from breast to breast in the EIT technique. This has also been shown by Amato and his group, and once again, it's not true to assume that this zone here, or region of interest, represents the same that is represented here. So, however, you have had several times the chance over the day to really realize that there's a difference between inflation and deflation. And that it works, I would like to show you with work that has been done by Ines Frerichs in Göttingen. And here she has shown what happens while using EIT technique, inflation and deflation limb of the pressure volume curve. And you can see the same. There is more and homogeneous distribution of aeration at the same pressure level on the deflation limb when you compare it to the inflation limb. So this is just, I want to skip that, but I left it in. This is to show you one of the problems of EIT technique as well, because EIT changes can be induced either by fluid shifts or by volume shifts with regard to gas volume. So it can be a fluid shift change or a gas volume shift change. You can even use EIT technique to measure extravascular lung water and edema, which has been done and performed in this study, with a higher accuracy than a thermodilution technique. And this is to speak now shortly about another technique, which is called extravascular lung water measurement. Aims in quantifying extravascular lung water, can be performed at the bedside, can be repeated, quite low costs, low distress for the patients. I don't want to go into details. We have some numbers which indicate more or less normal extravascular lung water, and we have done some studies in pigs looking at the changes of non-aerated lung volume and the reduction of shunt. There is a quite good correlation, and it's quite comparable to the extravascular lung water changes. So extravascular lung water and delta non-aerated volume show a quite good correlation, but the correlation of shunt when compared to non is even better. So again, what we did in this study, we looked at the changes while using different PEEP levels. You know these PEEP levels, 21, there is a shift. And all these studies have been performed in the same animals as you have seen before. So once again, extravascular lung water, while increasing PEEP from 0 to 21, there was a marked reduction of extravascular lung water. And again, what we find also in this study, if you look at the changes in elastance, though there was a change in elastance of the total respiratory system, however, there was very much more changes in elastance and a stable elastance with the chest wall, but the changes were related to changes in lung elastance. And now the most important information if we talk about extravascular lung water measurement. And what you can see here, this is tissue volume. This is consolidated lung area. So you find no correlation at all between extravascular lung water changes and consolidated areas, which means this technique does not at all allow you to draw any conclusions to consolidated lung areas. And Luciano has skipped one slide before, and the reason for that is he has markedly and nicely shown in this slide, because in these regions you have no perfusion. And where you have no perfusion, an indicator technique which is perfusion dependent will not work. So finally, I would like to close my talk by I think I tried to summarize a little bit CT applications, and I would try to summarize, and I know that it's not complete, a little bit EIT and extravascular lung water measurement. Measurement can be performed at the bedside, and they can be repeated in both directions. Several studies have shown good correlation between EIT and CT changes in aeration. That's quite true. it is not possible to discriminate between gas and fluid volume changes while using the EIT technique. EI3 describes not the real anatomy, but a cylinder, and actual development from EIT techniques and interpretation is far away from any standardized protocol or tool for analysis. Extravascular lung water shows a good correlation between gravimetric water content, shunt volume, and aeration. However, and it shows a good correlation between PEEP-induced decrease in non-aerated lung volume. However, it shows a lack of correlation with increased lung tissue mass or consolidated and atelectatic lung areas. I thank you very much for your interest.